Hi all, today we are going to discuss about errors in dynamometer types wattmeter and how to remove those errors in the dynamometer type wattmeters. So before proceeding to this, last class we have seen that in order to construct the wattmeter, the dynamometer type instrument basically have two coils. One coil is called as the current coil, I am representing by Cc. Another coil is called as the pressure coil. That pressure coil is connected with some series multiplier, some voltage, let us some resistance. That resistance value, let us take it as Rv. So we have seen in the last class that we have assumed that whatever this pressure coil circuit is, they're purely resistive, and we also assumed that whatever there is a voltage drop or the resistance of the current coil is assumed to be 0. So in that case, I can tell that my whatever the voltage is their supply voltage, same voltage will reach your load, that is equal to V. The current that is passing in the pressure coil, as it is purely resistive, so it will be in phase with this, and the current that is passing in the current coil, that will be nothing but your load current, or I am simply representing with I, and the angle between these, that I am representing by phi. So in that case, the amount of the deflecting torque that is produced is equal to the current that is passing in the pressure coil multiplied by current passing in the current coil multiplied by cos of the angle between these two currents into dm by d theta. This is the rate of change of mutual inductance with respect to change in the deflection angle theta. So we have seen that this value will be nearly made equal to constant. So this value we can take as a constant. So the value of this IP, this I can represent in terms of the voltage. This is voltage divided by resistance of my pressure coil circuit. The resistance RV plus the resistance of this pressure coil together, let us take it as RP, resistance of the pressure coil circuit. So IC is nothing but equal to I. So this I can write as cos phi into dm by d theta, or otherwise this I can write as simply some constant K, because RP and dm by d theta are constant. This I can write as V into I into cos phi. And we know the controlling torque, that will be equal to some constant, some K2 times of theta. So finally the pointer will stop at a location when TD is equal to TC, or otherwise whatever theta is indicating, that theta is indicating some K divided by K2 into Vi cos phi. So this I can write as, if you can adjust the multiplication, so this I can write as the amount of the power that is measured, PM, will be equal to V into I into cos phi. This is what we have seen. But practically, we cannot neglect the resistance of the current coil. And similarly, the pressure coil practically will have some inductance along with the resistance. So which is neglected there. And because of the existence of the resistance, because whatever the voltage is coming at your across your pressure coil, that will not be same as your load voltage, because there is some drop across your current coil, that is not considered here. That also introduces some errors. Similarly, some other errors also introduced. So today class we are going to discuss about those errors and how to overcome those errors in practice. So first one, practically what happens, this pressure coil will have both inductance as well as the resistance. So let us assume the resistance that is there, that I am representing by total resistance, is Rp. This pressure coil is also having some reactance Xp. Then the resultant value, that will be equal to the Zp, that means impedance of the pressure coil. So let us assume this angle is beta. So as a result of this, what happens, if you are taking this as your voltage, the current that is passing in the pressure coil, that I can write as Ip, this will be lagging behind this voltage by this impedance angle, that is equal to beta. Let us assume your current that is passing, that is I, angle with respect to V is phi, but the angle between these two currents is not equal to phi now, so this will be equal to phi minus beta. That means angle is not equal to phi, so that is going to affect your reading. So how that will affect, so that we are going to see in today's class in detail. So let us proceed further. So first, starting with the error due to the pressure coil inductance. So we have just discussed now. So if you are taking this as your voltage, that is voltage across your pressure coil, I am taking as V. So practically we have seen that the current will be lagging behind this by some angle. So this I am writing as IP. It is lagging behind this voltage by some angle of beta. And this is my current passing in the current coil. IC is nothing but equal to I. So this is having a power factor angle of phi. So now what happened, the angle between the currents is not equal to phi now. So this will be equal to phi minus beta. And why this beta is coming, we have seen there, this is happening due to, because the coil of the pressure coil, that can be represented by two components. One is Rp, total resistance of the pressure coil, and Xp, total reactance of the pressure coil. And this resultant value, that gives my value of the Zp, and this angle is equal to beta. Because of this, it is coming. So let us go to the derivation now. So Td is equal to the pressure coil, current passing in pressure coil multiplied by current passing in current coil into dm by d theta into cos of angle between these two, that is phi minus beta. So this I can write as IC into V divided by ZP, because this IP, this I can write as V divided by ZP, because here the impedance is there, not the resistance. dm by d theta into cos of phi minus beta. So using this a triangle, so from this I can write as cos beta. So cos beta is nothing but adjacent by hypotenuse. So this will be RP divided by hypotenuse is ZP. Or otherwise, from this I can write my value of ZP is equal to, ZP will go here. So this will become equal to RP divided by cos beta. So this one I am just keeping here in place of ZP. So RP by cos beta into dm by d theta into cos phi minus beta. So now what happens, RP by cos beta, this cos beta will come to numerator. I have shifted here. And we know the value of IC, this IC is nothing but equal to I, since the current passing in current coil is equal to I. That is the reason this is coming into cos beta into dm by d theta into cos of phi minus beta. So from this I can calculate my deflecting torque, because we can see the RP is constant in practice, dm by d theta is constant. This will become equal to V into I into cos beta into cos of phi minus beta. Or otherwise we can tell that the measured power is V into I into cos beta into cos of phi minus beta. But what is the value of the true power? The value of the true power is V into I into cos phi. But this is not happening in the measured power. It is coming different. What is the reason for getting this? Because here extra term is added beta. Why the beta is coming? This beta is coming because of there will be inductance of this coil. Pressure coil will have inductance also along with the resistance. Practically this value is less compared to RP, but still it will be there, some value of the beta is there. Let us assume if the value of XP is equal to 0, then what happens? Because when XP is equal to 0, this ZP is equal to RP or beta is equal to 0. You substitute beta is equal to 0 in this. This will become cos 0 is equal to 1. Cos of phi minus 0, this will be cos phi. That means measured power will be equal to true power if the value of beta is equal to 0. But practically that doesn't happen. So same thing I am representing here. In the absence of inductance, beta will be equal to 0. So that equation 1 becomes Vi cos phi. That is nothing but equal to true power. So here I am defining one term called as the correction factor. So the correction factor is a factor by which the actual wattmeter reading is multiplied to get the true power. So we can write that the true power is, I am multiplying the measured power with some factor that is called as the correction factor, that is used for correcting the value so that I will get my true value. Or this correction factor I am representing by CT. So from this equation I can write CT is equal to true power divided by measured power. So this true power is nothing but equation number 2 we have written here, and measured power is equation number 1, which we got Vi cos beta into cos phi minus beta. I have just substituted both. So let us proceed this one. So this I can write numerator I am keeping as it is Vi cos phi. Denominator Vi cos beta, this cos of phi minus beta, this I can write as cos phi cos beta plus sin phi sin beta. So now what I am doing, from this entire term I am taking cos phi cos beta common. When you take this common, this term will be 1 plus this term, because that will be divided by cos phi cos beta. We know this sin phi by cos phi will be equal to tan phi. Sin beta by cos beta will be tan beta. Here cos beta is there, cos beta is there. So this will become as cos square beta. So next step is coming here. So this will be Vi cos phi by Vi cos phi into cos square beta into 1 plus tan phi into tan beta. I think up to here it is clear to you. So here this numerator Vi cos phi is there. So denominator also having Vi cos phi. Let us use a different color for this one so that the confusion will not be there. So I am going to this. So this Vi cos phi that is coming in numerator, that will be cos phi crossed with the Vi cos phi in denominator. So this will come as 1 by cos square beta into 1 plus tan phi into tan beta. So here you have to see one thing. This value of 1 by cos square beta. What is this 1 by cos square beta? 1 by cos square beta. 1 by cos I can write as secant. So this will be equal to secant square beta. And we also know the value of secant square beta is nothing but 1 plus tan square beta. 1 plus tan square beta. So the same thing I have substituted here. So 1 by cos square beta is secant square beta, and the secant square beta is 1 plus tan square beta. I have adjusted in such a way. So practically what happens, the value of the beta is extremely small, the value of beta that is very small. So if beta itself is small, so we are to taking tan beta. Tan beta is small and we are making the square of that. So tan square beta, that value will be far less than 1. So we can write it as 1 plus tan square beta. So this I can write as approximately equal to 1. So that is the reason this tan square beta, so that I am replacing with 1 here. So this I can write as 1 plus tan square beta is 1 divided by 1 plus tan phi into tan beta. Because beta itself is small, tan square beta will become extremely small. That is the reason I have written this. So now I can finally write that this equation is nothing but correction factor or ratio of true power by the measured power. So this is Pt by Pm is equal to 1 by 1 plus tan phi into tan beta. So this I am rearranging the equations. So this from this I can write Pm will go this side. So 1 plus tan phi tan beta will come here. So it will be Pt into 1 plus tan phi into tan beta. Or this I can write as Pt plus Pt multiplied by tan phi into tan beta. So from this I am just rearranging. So this I can rearrange as Pt I am taking to the second side. This will become Pm minus Pt is equal to Pt into tan phi into tan beta. So we know the value of the true power. This true power is nothing but Vi cos phi. So that I have replaced here Vi cos phi into tan phi I can write as sin phi divided by cos phi, and tan beta I have taken as it is. So here again thing is that this cos phi will cancel out. So this will become Vi into sin phi into tan beta. So finally we got the error as V into I into sin phi into tan beta. Here you have to make one observation. So whatever the error is introduced, that is proportional to the beta. Because as the beta is increasing, tan beta increases, so the error increases. If beta is equal to 0, tan 0 will be equal to 0. So error will become equal to 0. Similarly, it is depending on another parameter along with beta, that is the power factor. As the power factor is decreasing, that means the value of phi will goes on increasing because power factor is cos phi. That means lagging power factor or lower power factor, the value of phi will increase, so sin phi will increase. That means error will increase. And this equation we have derived for the case of lagging power factor case. So for lagging power factor case, because we know the phi is positive, so that's why the error will be positive. That means the measured value will be greater than the true value. But if you are taking for the leading power factor case, because lagging power factor case, if you take, this is my voltage V, I am taking, this is my current I, this is my current IP, this angle I am taking as beta, this angle I have taken as phi. Getting it? So this direction I am taking positive, but this is for lagging power factor. For the case of leading power factor, what will be there? This is my voltage. So this is my IP. So here whatever beta is there, beta is positive like before. But now the current will be in another direction. This is I. This value is phi. This is for leading power factor. So if you are taking this direction, I am taking as positive, then here this has gone to this direction with respect to the voltage. So this will be taken as negative angle. So if you, entire equation you can substitute negative and C. Other option is whatever the initial equation come, you take the value of the value that is measured will be IP into current passing in the current coil into cos phi plus beta, and you make the same derivation, then you will get the final equation. This equation will come as minus Vi sin phi into tan beta. In that form it will come. So you can tell that the measured value will be less than the true value. Negative value indicate measured value is less than true value. So in order to avoid this error, because practically inductance cannot be avoided, so in order to avoid this error, so what we will do, we will go for compensation of the pressure coil inductance. How this will be done? So whatever the external resistance that is connected or the multiplier, it is separated into two small parts. So across one of the small resistance, we connect some capacitance C. So now we have to see what should be this value of capacitance C that should be connected, so that effect of inductance is completely nullified. So before proceeding, let us try to analyze the different components of this pressure coil circuit. This pressure coil circuit, whatever is the pressure coil that is having inductive reactance of L, let us assume that resistance is equal to Rp. Whichever external resistance is connected, that is having two components. One component is this small resistance, which is Rv minus small r, that is one component, and another component is R. So total value is Rv, or the total resistance of this entire circuit I am representing by Rp. That means this is having the combination of small rp plus capital Rv. together is a resistance. So if you want to calculate the total impedance of the circuit, so this I can write as, due to the inductance L, this will be equal to j omega L plus Rp is there, plus entire Rv is not connected because again there is a parallel combination of this one. So this resistance is nothing but Rv minus small r. So this I can write as Rv minus small r. So this is the resistance, plus there is a parallel combination of two things. One is R, that is having the parallel combination with Xc. So this I have to calculate. So let us try to expand this. How this will come? Because we know parallel combination of two resistance will be R1 R2 by R1 plus R2. So this I can write as R multiplied by Xc divided by R plus Xc, R1 R2 by R1 plus R2. So this I can write as R. What is the value of Xc? Xc we know equal to 1 by j omega c. So this I can write as 1 by j omega c divided by R plus 1 by j omega c. So when you further simplify this one, this will become R, numerator will be R divided by, here also I am taking j omega c common, so that j omega c I can cancel. This will become j times of R into omega c plus 1. So I want to remove this j from the denominator. So what I will do, I am just multiplying and dividing with 1 minus j into R omega c. Denominator also 1 minus j into R omega c. So now we know a plus b into a minus b. So that will come as a square minus b square. So let us take the numerator first. So this will be R multiplied by 1 minus j times of R omega c divided by a square minus b square. That means 1 minus j square R square omega c square. We know j square is nothing but equal to minus 1. So minus into minus become plus there. This will become 1 plus R square omega square c square. Okay, so this one I am directly substituting in the equation. So the value of the Zp I can write as Rp plus Rv minus R plus j omega L plus this equation that is coming here, R, when you multiply with this you will get this equation. So this equation number 4 I think you understood. So let us proceed further. So if the value of the circuit constants that are designed here, that means the value of R, C and all these things are so chosen that for the case of power frequencies, if I can make omega say c square r square, omega say c square r square, this is taken as far less than 1, so that my denominator will be simply equal to 1. Only numerator will be there. That means 1 plus omega say c square r square will be equal to approximately equal to 1. So this value is designed for the frequencies of up to 10 kilohertz, so that even when the noise or something is going through this or high frequency you are applying, then also this will not create any problem. So this value is designed, this will hold good up to a frequencies of 10 kilohertz, up to that much range it is designed. So this will be equal to 1. So I am just substituting in equation number 4. So denominator becomes equal to 1. So this equation becomes Rp plus Rv minus R as it is from here. J omega L will come as it is plus R minus j omega c r square. Okay. So here you can see this R is minus, this R is plus. So both will cancel out. So that is gone. So it will come as small rp plus rv, small rp plus rv plus j omega L minus j omega cr square. So this value of small rp plus rv, if you go up, let us go back to this. So we can tell the value of small rp plus rv, that is nothing but equal to rp. So I can directly write that one as rp in that equation. So I am going back there. So that I can simply write as this rp plus rv, this is nothing but equal to rp plus j omega L minus, because j omega I have taken common, this will be L. Here minus sign is there, so minus c into r square, because omega is taken outside. So here you can see there are two components. One is the rp, second one is L minus c into r square. Okay, those two are constituting your value of Zp. So that means Zp I can write like this. This is my value of rp. Let us assume the inductance is dominating compared to capacitance. So let us assume this I can write as L minus cr square. If capacitance is dominating, it will come in the second direction. So this gives my angle. This gives my final angle that I can write as the pressure coil. That angle that is made is now equal to beta dash. So this is the now impedance of your pressure coil. So now I want to make it purely resistive, because effect of inductance or capacitance that I want to nullify. How this will happen? This value of this L minus cr square, this will be equal to 0. So that imaginary component will go. So that we are going. So if we make the L is equal to CR square, so that equation number 5 becomes ZP is equal to simply RP. That means purely resistive, or we can tell that the value of beta is equal to 0 or error will be equal to 0. So practically one capacitor is introduced. So similarly, there can be another chance also, because we are connecting high value of resistance in the pressure coil circuit, there will be inter-turn capacitance is formed there. Even though it is very small value, but inter-turn capacitance is also formed. So that means the resistance whichever is there, that I can represent as RV, and one more capacitance term, some Ca also will be formed there. So this effect is generally this effect of this inter-turn capacitance, this is opposite to the inductance of the coil. So that's why actually it will decrease the effect of the inductance. Practically the value of this capacitance will be negligibly small. So that's why this effect can be neglected in practice. That means the effect of capacitance is neglected in practice because that value is very, very less compared to the effect of the inductance. So then coming to error due to the connections. So till now whatever we have analyzed, we have assumed that the current coil resistance is equal to 0, but practically it is not equal to 0. And we are also assuming the supply voltage is equal to load voltage. That also doesn't happen. So let us see what are the different possible connections and how they will introduce the errors. So first possible is, if you take any wattmeter, it will have 4 terminals. One is M, L, third terminal is C, fourth terminal is V. You have to interconnect them. Let us assume this M and C are connected together. This V is connected to the negative terminal. That means you can see the pressure coil is connected across your supply. So now the amount of the voltage that is measured by your pressure coil will not be equal to simply equal to the load voltage V. So it will be something else. So what is this value? Because when the current is passing through your current coil, because current coil also will have some resistance. The current coil also will have some resistance RC. Because of this, I into RC is dropping across this. So we can tell that voltage measured by pressure coil is Vs. That Vs is not equal to V, because it is also measuring the drop across the capacitor, or otherwise the power measured will be sum of the load power plus the power consumed by current coil. So in order to avoid this, what I can do, instead of connecting C to M, I can connect C to L. This is the second connection that is possible. V will be connected here. That means here the pressure coil is connected across your load. So now what is happening, whatever the current is drawn by your pressure coil, that same current is passing through your current coil also. This is my load current. So the current coil is carrying both. As it is measuring the current passing through the pressure coil also, what does it indicate? It is measuring the power consumed by the pressure coil also. Both are added. Because practically the power consumed is not equal to 0. So some error is introduced. So let us see what is that error that is introduced. How to overcome that one in practice. So first I am going with the first connection. Pressure coil is connected across your supply. That means M and C are interconnected together. So this I can write as current passing through the current coil. If we are taking this as IS, this current passing through the current coil is nothing but equal to this IC. This is equal to I only simply. So that I am writing I. Then voltage across the pressure coil, that will be equal to supply voltage. This supply voltage is nothing but V plus what is a drop across this current coil. Let us assume the resistance of the current coil I am writing as RC. This will be V plus I into RC. Or otherwise, the measured power will be, what is a true power? That is V into I into cos phi plus the power consumed by this that current coil also. So this will be power consumed by the current coil, that I am writing as PCC, which is nothing but the current passing through the current coil is I square multiplied by resistance of my current coil. Okay, so practically measured power is PT plus I square into RC. So here you can see PM is not equal to PT because of I square into RC. Practically the resistance of the current coil is very small because we cannot decrease it further. So if the current is less, so I square will be less. So if current is less or the amount of the current is less, so in that case PM will be approximately equal to PT. That means this connection is preferred when the value of the current is less, so that the PM will be approximately equal to PC, or the error introduced by this I square RC, that will be decreased. So this connection is used mainly for the low current applications wherever the current is less. So there is one more connection that is possible. What we will do, the L is connected to C. So if you are connecting like this, so now what happens, the current passing through the current coil will be IS. This IS is having the sum of two currents. One is I and another current is IP. So two currents are passing through a current coil, IL plus IC. Voltage across coil is nothing but V now. So total power that is measured will be V, but current coil is measuring both currents. That means one more extra power it is measuring due to the pressure coil, that I can write as PP, that is power loss in the pressure coil. So this will be nothing but the current passing through this one square multiplied by resistance of the pressure coil circuit. So I can write it as RP. So in this case also, it is not equal to the true power is not equal to measured power. So extra thing is there, that is added IP square into RP. So if this, how to decrease this one? That means IP square into RP. Okay, so I have to either decrease IP or increase RP. But if you are decreasing IP or increasing RP, so in that case what will happen? The amount of flux produced is decreasing, so the amount of torque will further decrease. So that is not preferable. So which cases this can be used? Let us assume if my value of the true power or the load power is extremely high, then in that case this can be neglected. Or otherwise I can tell that if my value of the load current is very high, so this whatever the current passing through the pressure coil is negligibly small compared to I. So in that case I can take my IS, which is the sum of I plus IB is approximately equal to I, or I can take measured value is approximately equal to true value. That means this type of connection is preferred where the load current value is very high, or otherwise the load power is very high compared to power consumed by the pressure coil. So let us take the example. In this previous case only, I am assuming my load is equal to 0. That means under no load condition, let us assume I have activated my energy or this wattmeter. So wattmeter, even under no load condition, the value of the IS, current passing through your current coil, that will be nothing but equal to IP. And voltage across your pressure coil, this will be nothing but equal to V. This V is nothing but Vs minus drop across the current coil, or it is nothing but equal to the load voltage. So here also some current is consumed. So which this current is indicating what? This is indicating the power consumed by your pressure coil. That means the power measured by the wattmeter under no load condition, that will be nothing but equal to I square into RP, or that is nothing but equal to power consumed by the pressure coil. So if you want to remove the error in this type of connection, what we can do? So make the connection like this. That means if you are taking the terminals M, L, C and V, so make the connection between L and C. So first you don't connect your load, then measure the power. That gives my value of PP. Then you connect the load. Once you connect the load, then you can measure the power. So what you have to do, you can calculate the true power is equal to what is the power that is measured under loaded condition when load is connected, minus what is the power that is indicated by your instrument under no load conditions. So this is possible in the case where you can disconnect the load before measuring the power, but practically it may or may not be possible. So in that case, what is the other way how we can nullify this? Okay, so wherever this accuracy is required more, so what I have to do, that error introduced due to pressure coil current should be nullified automatically. So for that what we will do, we will use one compensating coil in the circuit. What is meaning of the compensating coil? Whatever is the current coil is there, this current coil will have two coils. One coil is this current coil, and there will be one more coil will be there. Let us take with some different color. So one more coil also will be there, that is wound above this one. That means two coils are there. So how these will be connected? So this is connected like this. So this is going to my pressure coil. That means the current carried by this one is nothing but pressure coil current. So this is connected to your supply. This is nothing but equal to IS, that is equal to current that is passing in the load plus current passing in the pressure coil, because this is nothing but I, because I is going to your load. This is my value of the supply current. So here the current that is passing is IP. So what is the current passing through this coil? So this coil, the current that is passing is I plus IP. So this is passing in this direction. You can see this direction. This coil is wound in the opposite direction to that, and I will make the number of turns is equal to same. So that because we know MMF is equal to number of turns into current passing through each turn. So the MMF produced by both will be same. And here the current that is passing this IP is passing in opposite. Now what happens? These two fluxes are produced in opposite direction, so they will counterbalance, or otherwise we can tell that the net flux produced by your current coil will be I plus IP minus IP, because through this IP is passing. I plus IP minus IP will be simply equal to I. So in that manner, the effect of the pressure coil current in measurement can be nullified. So that I am writing it. The current coil basically consists of two windings, each having the same number of turns. So one winding, whichever winding is connected through this connected to your supply or to the load, because that should carry the rated current, so that will carry the current I. Whereas whichever coil is connected to your pressure coil, that need not be thick because it has to only carry the IP. So it is made up of thin wire. But thing is, both will have the same number of turns. They are wound in opposite direction. That means they produce the flux in opposite direction. So what will be the result of this? So the net flux produced by this coil will be only due to the load current I. The second one is nullified by both. So using this, what happens? The error introduced will be equal to automatically 0. So there can be another type of error that can be due to the eddy currents. So how the eddy currents will come? Because we know huge value of current is passing through your current coil, because basically your instrument will have one fixed coil which will be wound on the stationary part, one will be wound on the rotating part. So we know that the current carried by the current coil is more, that's why it is kept on the stator. So as the current is more, the amount of flux produced is also more by that. Because in the rotor, we have to decrease the weight of the rotating part, so automatically the current is less, because in order to decrease it, the amount of MMF produced by this is also less. That means this current coil, whatever current is passing, if you are connecting to the AC, that will produce the time varying flux. So that will link with the neighboring metal objects. That means in the stationary, near to the stationary part, if you keep any metal object, that will induce some voltage. So to understand this, let us go to this diagram. From this we will try to understand. Let us assume the voltage I am taking as V, the current passing in the pressure coil, because let us assume it is completely compensated using the capacitor. So current is in phase with the voltage, that produces my value of the flux phi P. Now coming to the current coil is producing a flux phi C due to the current I. This current I is lagging by some angle phi. So due to this phi C, which is time varying, EMF is induced in the surrounding metal parts. So always we know, as per the transformer action, the EMF will be lagging behind this flux by 90 degrees. So that I have represented here, that I am writing as EE. Let us assume that current that is produced, or eddy currents, due to this induced voltage, let us assume it is lagging by some little bit angle, because practically there will be nearly resistive, little bit angle will be there. Because of this IE, phi E is passing. So now what happens? The net flux that is produced by your current coil will be having two fluxes. One flux is phi C, another flux is phi E, which is produced due to phi C only. So the vector sum of these two, or phasor sum of these two, that gives my resultant value of flux. So that's why what I am doing, I am drawing a line parallel to phi E. So phi C plus phi E, that will be my resultant flux produced by your stationary part. So here you can observe from here, the value of this phi R, the length of this phi R will be less than phi C, because you can see here, because phi E is coming like this. And second one, the angle between the two currents is not equal to phi now, because you have to take the resultant value of the flux, because torque is produced due to fluxes. So now you have to take the angle between phi R and phi P. You can see that is becoming equal to phi dash. That means phi is also increased, and the value of the flux, resultant flux, is also decreased. So because of these two effects, what happens? The net torque will be decreased. So that I am representing here. So the total torque is proportional to phi P, current passing in pressure coil, resultant flux produced by the current coil or the stationary part, multiplied by cos of the angle between these two. So between these two, I am taking that angle is equal to phi dash. This phi dash is less than or greater than phi, because you can see in this case, lagging power factor case, this angle is greater than phi. So that's why it is greater than phi for lagging power factor. Or otherwise, we can tell that this power is less than the true power case, because the reason is the resultant value of the flux, this is less than previous phi C. Similarly, cos phi dash is less than cos phi. Or otherwise, we can tell that measured power is less than the true power for lagging power factor. So this will be opposite for the case of leading power factor. So how to avoid this error? So to avoid this error, what we have to do? Why this is happening? This is happening due to the eddy currents. So I have to make my eddy currents 0. So when the eddy current will be 0, when there are no solid metal parts. So along with the solid metal parts, the eddy currents will also induce in the conductors which are very thick. Because your current carrier is made up of thick conductor, so that's why eddy currents can be induced in the current coil itself. So that's why we have to make that current coil with a stranded conductor. So I'm just summarizing it. The solid metal part should be avoided in this instrument, and the current coil is made up of the stranded conductors to decrease eddy current within the current coil. So this is the reason that is done. I hope it is clear up to here. Then error due to the vibration of the moving system. So if you see the instantaneous torque equation, to understand it, let us assume this is my instantaneous voltage. The current is lagging behind this voltage by some angle. So let us assume this is my current. So now the resultant value of the torque will be the product of the voltage and current. If you are assuming that is purely resistive pressure coil circuit and current is there. So product of these two, because here you can see the current is negative, voltage is positive. So product of these two will be negative. And here in the second half it will be positive. Similarly here it is negative, here it is positive, here it is negative. So this is the power P, or nothing but equal to the torque. So torque, whatever waveform comes, that waveform will come similar to this one. That will be similar to this one. So here you can see the torque. It is having negative part as well as positive part. Your supply frequency, it is completing one cycle in this. But you can see in this one cycle, this power or torque is completing how many cycles? 2 cycles. That means this instantaneous torque on the moving system, that varies cyclically at twice the supply frequency of the voltage and current. So if any part of the moving system that is there in the moving system, such as spring, pointer, etc., because every mechanical device will have some natural frequency of oscillation. So if that natural frequency of oscillations are coinciding with the 2 times the torque frequency, or otherwise the equal to torque frequency or 2 times the supply frequency, then resonance happens between the moving part and your supply. So then they will start vibrating at a huge amplitude. When they start vibrating at huge amplitude, the pointer will start moving around its final position. We cannot take the reading properly. So that's why it should be avoided. So practically all the moving parts should be designed in such a manner that their natural frequency of oscillation should be greater than 2 times the supply frequency. Because why 2 times the supply frequency? It is nothing but equal to frequency of torque pulsations. So there can be one more error. That error is due to change in the temperature. So whenever the temperature is changed, because with respect to the season also temperature changes, along with that when the current is passing through the current coil or pressure coil, because I square R loss will be there, that also produces the heat. So now the effect will be, there will be effect with the coil resistance also. Similarly, the control spring, whichever spring is used for producing the control torque, that stiffness also depends on the temperature. So practically what happens, these two are actually in the opposite direction. So practically they will cancel each other. So the effect is negligibly small. In order to provide the more accuracy, practically whatever that series resistance that is connected in the pressure coil circuit, that resistance is connected in such a manner that it is insensitive to change in the temperature. That means that compensating resistor should be like that. It is not affected so much due to temperature variations. So in that case, the effect of temperature errors will be almost nullified. So then there can be error due to the stray magnetic fields also. So we know that as the operating field of this electrodynamometer type instrument, here there is no permanent magnet. Flux is produced due to 2 coils only, and that too, whichever coil is on the rotating part, we cannot pass more current due to weight concern on the rotor. That means the amount of the flux that is produced, working flux, will be very less in dynamometer type instrument when you compare with PMMC type instrument, permanent magnet moving coil type. So as it is very weak, so care must be taken that external magnetic field will not come and interfere with the circuit. So in order to avoid the external magnetic field from entering your circuit, either I can go for laminated iron shield. These are generally used for portable laboratory type instrument, or I can go for the steel casings as shield. Some steel casing is used. These are used in switchboard mounted type wattmeters. But in both cases, there will be a problem. Again, this is a metal part, because this metal part is placed near the current coil. So what will happen? Eddy currents are induced in this. That eddy currents will introduce the errors due to eddy currents. So if wherever you want the precision type wattmeter is required, because this problem of eddy currents are there, so that's why generally these shields are not used. We go for another mechanism called as astatic system. What is the meaning of astatic system? I am just explaining with this diagram. What will happen? Whatever your circuit is there, that means the set of fixed coil and the moving coil, they are divided into 2 sub-circuits. Both are independent magnetic circuits, but both are kept on the same pointer. They are kept in the same pointer. You can see both are placed very far. So what will be there? This fixed coil is divided into 2 parts. Moving coil also divided into 2 parts. So fixed coil, this upper part, let us assume the current is passing in this direction. Upper part, the current is passing in this direction. So I will take care that the lower part, the current will pass in opposite direction. If current is passing in opposite direction, the flux produced by lower side is in one direction, top side is in another direction. But I want the torque produced by both coils should be in same direction. How can I get it? Let us assume in this coil, let us assume the current is passing some particular like this. So in this coil, the current should pass like this in the moving part also. That means in the pressure coil also. So what will be the result of this? Because you have reversed the current direction of both the coils, so torque produced will be in the same direction. If you are reversing only one current, then problem comes. torque will be opposite. So here both the torques are produced in the same direction. So pointer will move. So let us assume some external magnetic field is entering. So external magnetic field, it will add the field in one of this magnet, but second one the magnetic field is opposite direction. That means it will subtract. That means let us assume some external stray field is coming here. Some external stray flux is coming here. Let us assume the stray flux is adding to this flux. So let us assume it is adding in this one. So what will happen? The net flux is increased in this one. But here what will happen in this case? The net flux will be decreased. So resultant flux is decreased. So here the flux is increased, so automatically torque is increased here. But here what will happen? The torque is decreased. So effect is just 100% opposite to both and equal magnitude. So the effect of this stray magnetic field will be nullified. So that's why this is called as astatic arrangement. So let us try to summarize this one also, then we will stop this lecture. So they are manufactured to have the astatic type of system. So astatic system, this is constructed with two similar sets of fixed and moving coils. They are mounted on the same shaft. Both fixed coil carry current in the opposite direction. So same will be the case of moving coils, such that the torque that is produced by both will be in the same direction. So as the field produced by the top and bottom coils are in opposite direction, any external stray magnetic field will increase the field in one coil while decrease the field in another coil. So what will happen? The entire effect is nullified. So I hope whatever errors we have discussed and how to overcome them in this lecture are completely clear to you. If you still have any queries, you can leave your comments in the comment section below. I will answer to your queries from there. Thank you. Thank you very much.